All right. Hello. I'm Mickey, and I am once again talking about the motion of a free rigid body from the perspective of mechanics on Lie groups. Last time we talked about the Lagrangian side, and today we're going to talk about the Hamiltonian side. So we got, so last time, just a refresher, we were working with this Lagrangian, um, which is in what are called body coordinates. So these omega 1, 2, and 3 are angular velocities around the principal axes of inertia of the body. And then I1, I2, and I3 are the moments of inertia around principal axes. So when you use the principal axes basis, which moves with the body, the Lagrangian has this really simple form. It's an isolipse. So okay, if we want to uh, write a Hamiltonian form, well, first, what do we normally do? We take the partial derivative of L with respect to velocity to get a momentum, which is conjugate to the position coordinate Q. And we're just going to do the same thing here. We're going to say the L, the omega is, or pi, where this pi is the body angular velocity. This is just pi omega. Uh, Pi is just uh, the moment of inertia tensor and principal axes spaces, uh, which is just like a diagonal matrix with I1, I2, and I3 on the diagonal. Um, Now, since the Lagrangian is only kinetic energy, we basically just get to rewrite this in terms of the pi variables, find our Hamiltonian, which turns out to be pi1 squared, pi2 squared, 3 squared, 2 over I3. Okay. Well, this is our energy at least. Um, but is it really like, can we really do Hamiltonian mechanics? Because we're in R3, and Hamiltonian mechanics is usually thought of as taking place on symplectic manifolds, which are even dimensional. Now, it's true that these are just the momenta, but they're in body coordinates, and it's not really clear what the body coordinates for um, the positions would be. And in any case, it'd be nice to stick to three variables instead of six if we could. So, although we have a symplectic form available to us, we're still going to try and come up with a Poisson bracket. Okay, how we're going to do that is first recall that the Poisson bracket, what we really want it to satisfy is this. Okay, so we're just going to calculate what F dot is and then see if we can sort of shape that into a Poisson bracket. So F dot equals dF dP times U dot, just by the chain rule. This is dF dP dot E cross omega. And the reason, remember last time, the actual Euler equations that we got were d dt I omega equals I omega cross omega. And using that I as I omega, we just get the P dot is this. Okay. Now, if you take a look at the Hamiltonian and you look at its gradient with respect to pi, you'll just see that its gradient with respect to pi is just omega. So we can actually rewrite this like that. Okay. And I'm going to use the same triple product identity that I mentioned last time. Uh, just sort of, you know, move everything over by one and cycle it around at the end. And same thing. So this is, well, and then I'm also going to flip the order so that the order here is the same. But it's going to be F dp times H dp. So the negative sign is because after cycling everything, I swapped the order. So just so it matched over here. All right, so I pick up this minus sign, which in the general theory, depending on what system you're talking about, which Lie algebra you're in, whether or not there's a plus or minus sign does actually matter. Uh, but I'll talk about that in a video on the general picture. For now, we'll just keep it like this because this is a convention. Okay, so what does the Poisson bracket satisfy? It satisfies the Jacobi identity. It satisfies bilinearity and skew symmetric. And okay, well, what about this object? It's clearly anti-symmetric because there's a cross product right here. It's also bilinear because the dot and cross products are both bilinear. And the cross product satisfies the Jacobi identity. And since this dot product right here, it's really just picking off one component at a time. This is also going to satisfy the Jacobi identity. Okay. So we're actually going to define our bracket as this. So f of h at pi equals that. Okay. So this type of bracket here on a Lie algebra is called a Lie-Poisson bracket. I think Sophus Lie actually discovered this. They say he discovered it in the 1880s or whenever it was that he was working. And it wasn't for a long time that people actually realized he had sort of come up with this Poisson bracket structure on Lie algebras. And I think it was second half of the 20th century that people started to notice that. But okay. So I got this here and satisfies most of the properties of the Poisson bracket, except it's not non-degenerate. Now, Poisson bracket doesn't have to be non-degenerate, but in the usual symplectic mechanics formulation, you get the Poisson bracket from a symplectic form, so it's going to be non-degenerate. So what that means is f h equals 0 for all h implies f equals 0. And the reason for that, just a reminder, is that f h equals the symplectic form acting or taking as arguments the vector fields corresponding to f and h, where xf, or if you contract xf with the form, or with the symplectic form, it equals the differential of f. This is just the definition of xf, of the Hamiltonian vector field corresponding to f, and the Poisson bracket satisfies this. Or you can see it, you can talk about it being defined like this, because the symplectic form is non-degenerate. Poisson bracket is non-degenerate. Okay, but we don't have a symplectic form on R3, which means there's going to be a degeneracy. And it's pretty easy to see what it will be. You take c equals 1/2 squared. Then its gradient will just be c equals pi. And if you just stick that in here, then you'll have negative pi dot pi times grad h. I'm just going to start writing grad this way. This term's perpendicular to pi since cross product of pi with something, so pi dot this equals 0. Cool. Now, this is pretty unusual. We have this conserved quantity that's conserved no matter what the Hamiltonian is. Um, I didn't make any statement about what H was here. It's just zero automatically. So constants of motion like this are called Casimir invariant. Or sometimes just called Casimir functions. Um, and yeah, so now if we want to get a nice sort of visual picture of what's happening with the dynamics, we just have to note that C is a constant of motion and H is a constant of motion. And they both form surfaces in R3. So um, a point in R3 will be, on the intersection of a particular level set C and H, and it'll just move along the intersection of those two level sets. So a level set of C is going to look like a sphere, and a level set of H, did I write it? Yes, it's just going to be an ellipsoid. I'm going to, let's see, draw a very sort of eccentric ellipsoid to make it clear. Okay. And so the particle, or it's not a particle, but if you think about it as like a particle moving in R3, it'll have to move along this sort of curve here or another one here. And if you think about different energy levels, sort of all the different energy levels, um, basically just sort of all the different uh, energy ellipsoids you can have, uh, end up getting this picture that is a little tricky to draw, but it's in my channel icon. Want a better visual. And this diagram is also in, I think, every mechanics book. So it's not hard to find a better drawing, but I'm going to try anyway. Yeah, the point is just that there's these four elliptic fixed points and then these two hyperbolic fixed points. Um, yes. Okay. So the okay. So I mentioned already we don't have a symplectic form. Now, there is a way we can still turn this into a symplectic geometry. Well, we can formulate this as a symplectic geometry problem. Um, and to do this, well, we notice that there's these spherical invariant manifolds. And spheres, since they're two-dimensional oriented surfaces, they have an area form, and the area form can just be our symplectic form. So that suggests we can sort of reduce the problem down finally to like minimum dimensions for a Hamiltonian dynamics problem, like a two-dimensional problem, but just on a sphere. Okay, so that's what I'm going to do now. The sphere. Okay. Now, I'm going to start by saying I don't think this reduction actually helps you solve the problem because uh, the Euler equations, as they stand in three variables, can already be solved analytically. Uh, but as we'll see later, it's just good to observe that the level sets of the Casimirs are these symplectic manifolds. Okay, so first we're going to write our bracket in a slightly different way. So we know it looks like this. Spoiler, but And pi, as I already mentioned, is just the gradient of our Casimir C. So this is just this. It's also worth mentioning that any smooth function of a Casimir is another Casimir. Um, but this Casimir here, I mean pi squared over 2. Okay. Now, since we're talking about symplectic forms, we want to write this somehow as a form. And the way to do this is you can just verify by just uh, sort of a exercise in determinants that it works out to this here. And that means that actually our Poisson bracket, you can think of it kind of as being a volume form. Okay. It's just a volume form. This equals this. There is a paper actually by a scientist at the University of Chicago named Nambu, who sort of described these volume form Poisson brackets. And he described the situation as being Hamiltonian mechanics with multiple Hamiltonians. So Hamiltonians and Casimirs. He didn't, I don't know that he actually called them Casimirs, just called them extra Hamiltonians. And the paper was about how you can have statistical mechanics in this framework here. It's a short paper and it's a good read. But yeah, so that's sort of the approach we're going to be following. So we have this right here, and we want to reduce it down to these spherical level sets. So that means we should use spherical coordinates. So let's say pi1 equals, it's going to be root 2c sine b cos theta. Pi2 will equal root 2c sine b sine theta. And pi3 will equal root 2c cos theta. Okay. Now, we're going to try and write this in sort of like dc, d phi, d theta. So this is going to be our spherical coordinate. C will sort of be our radius. Okay. So lengthy calculation incoming, but I1 equals, okay, so this is going to be 1 over root 2c, and then chain rule, we're going to times 2, but then we'll have a 1/2 from the exponent of 1/2 here. So this is going to be 1 over root 2c sine phi cos beta dc. Okay, now plus root 2c cos phi cos beta d phi plus root 2c, actually minus root 2c sine phi sine theta d theta. Okay. Then dp2 equals 1 over root 2c sine phi sine theta dc plus root 2c, and this is going to be cos phi sine theta d phi, and then plus root 2c sine phi cos theta d phi. Oh, that's supposed to be d theta. And lastly, BP3 equals um, 1 over root 2c cos phi dc plus root dc or root 2c uh, sine phi phi negative. Okay. So we just want to get our volume form back in terms of c, phi, and theta. Okay, so going to start calculating this, wedge this now. Okay. This is equal to, okay, so the C term dies because the wedge is antisymmetric. So C phi is going to be, um, okay, it's going to be sine theta, cosine theta, or sine phi, cos theta, sine theta. But then the next time we multiply, we're going to do the phi times the C, and it's going to be cos sine again, except the order of phi and C will be flipped. Then when we flip that order, we can just cancel. I'm just going to write that out anyway. In case that wasn't clear, but it's going to be or sine cos dc wedge d phi minus uh, sine cos phi sine theta cos theta d phi wedge dc. Okay. Um, yes. So if you just swap these two right here, you'll pick up a negative sign. This whole part will cancel. Okay. Now we have the dc d theta term. This is sine squared phi cos squared theta dc wedge d theta. Next, we have the phi theta term, which is going to be 2c sine cos phi cos squared theta d phi d theta. And then which one? We've done that and that. No, we haven't done that one. So but we've done this and this, and we've done this. So we still have to, okay. So then we have sine squared. Oh wait, no, we did do that one. Okay, so now it's just the thetas. This is sine squared phi sine squared theta. Yeah, okay. And there's a minus sign. And there's minus 2c phi cos phi sine squared theta d phi wedge d theta wedge d phi. Okay. Now, if you swap these two and combine terms, you'll get sine squared phi c wedge d theta. And then if you swap these two right here and then combine terms, you'll get plus 2c sine phi d wedge d theta. Okay, cool. Now, last step is just to multiply or wedge dp3 onto this. So we'll get Let's see. One wedge DP, two wedge DP, three equals 2c over root 2c sine phi cos squared phi d phi wedge d theta wedge dc. That is a beautiful phi I drew there. Okay, then minus root 2c, it's this one here, sine cubed theta, sine cubed phi, sorry, um, dc wedge d theta wedge d phi. Okay, now we want to combine these, but we got to get the order straight. So um, this we can just cyclically move c back to the front and scoot the other two and not pick up a sign. And then this one we can just swap phi and theta and we switch the minus to a plus. And then this term right here actually cancels down to 2c. So we'll get 2c sine theta cos squared theta plus sine cubed theta dc wedge d phi wedge d theta. Awesome. And you can just factor out a sine squared plus cosine squared. So this is 2c sine phi dc wedge d phi wedge d theta. Okay. And now let's say we want to stay on one of these spherical level sets of the Casimir. And c is constant. And we're really just going to be worrying about these phi and theta terms. So f h d3p goes to f h. There's going to be a 2c, and we're only going to have this last thing here. It's going to be sine phi wedge d theta. But we can, if we want to make this look like the canonical form of the symplectic form, then if we say, we can just put this in here and make it a cosine. So we get root 2c f h equals d theta wedge d cos phi. Or sorry, I don't know why I put an equals there. It's just times. This is the area form now, right? Because when you take the derivative, you pick up a negative sign, but I swapped the order. So, okay, our bracket went from being a Poisson bracket volume form down to a Poisson bracket area form. Okay, so here we go. We're on a symplectic manifold. This is a symplectic form. And we have it's an area form, so it works as a symplectic form. We can fix C and then just sort of change the units so that we kind of can ignore this factor and starts to look like normal Hamiltonian dynamics again, except it's on a sphere instead of a cotangent level like normal. And our canonical position and momentum pair, instead of a position and a momentum, you have this conjugate pair. And take care, because on the sphere, you can't really, sometimes you can get away with saying something like T is proportional to Q dot. in normal Hamiltonian mechanics, but because you're on a cotangent space, but you're not really able to make such an easy identification because it's on a sphere. But yeah, okay. So as I mentioned earlier, this reduction is kind of cool, but it's not really practical. It introduces a coordinate singularity because it's spherical coordinates, and you can solve the problem without using it. But I thought it'd just be good to show that there's still the usual symplectic geometry happening somewhere in the picture. Okay, so that's basically everything I wanted to say for now about the rigid body or the free rigid body. Um, in the next video, I think I will be talking about sort of the general overall picture. So on the Lagrangian side, instead of Euler-Lagrange equations, when we're working on Lie algebras, we'll have what are called Euler-Poincare equations. And then dual to this, we'll have a Hamiltonian picture with what are called Lie-Poisson brackets. And I think in there, I'm going to give an explanation of how you can view other systems like the perfect fluid um, as examples of this type of formalism. So I hope you enjoyed watching, and I will see you next time. Thank you.